Okay, in this lecture, we're going to do various points about quantifiers, some of which you've seen partially before, so it'll be some of it review, but don't stop paying attention and count this out because we will definitely go deeper than we did before in chapter 1. Okay, so the first thing I want to do with you is negating statements with quantifiers. Okay, so let's suppose that we have a statement like this. For all x in D, Q of x. So that is saying that Q of x is true for every x in the set D. Okay? All right, I want to write down what is the negation of that. Okay? So maybe we should do an example. What if D is the cars in parking lot number 2? And what if Q of x, I should say the set of cars instead of just the cars. There we go. Okay, so D is the set of cars in parking lot 2. And let's say that Q of x is the statement x is blue. Then this statement right here says every car in parking lot 2 is blue. It says for all x in the set of cars in parking lot 2, x is blue. So in other words, if x is a car parked in lot 2, then x is blue. Or in other words, every car in lot 2 is blue. Okay, that's what that says. So what would be the negation of that? A lot of people get this wrong their first try because they think maybe the negation is this. But that's way too far in the other direction. That says for every car parked in lot 2, not Q. So in other words, this says every car in lot 2 is a color other than blue. Or another way of saying that is no car in lot 2 is blue. So think about this for a minute. We go out to lot 2 and I say to you this purple sentence there. Let me erase the negation symbol. We go out to lot 2 and I say to you, oh look, every car here is blue. And you look at me like I'm crazy. And you want to explain to me that I'm wrong. Okay? Would you explain to me that I'm wrong by saying, no, there's no blue cars in this parking lot? I mean, that might be true that there's no blue cars, but is that what has to happen in order to show me that I'm wrong? No. In fact, think about it. If we go to the parking lot 2 and I say, once again, oh look, every car here is blue. I want to ask you a question. How many non-blue cars do you need to find to prove me wrong? Isn't it true that you only have to point out a single car that is not blue? If I say all of these cars are blue, and let's just assume that I'm wrong. I mean, I suppose it's possible that it could be a whole parking lot of blue cars, but let's assume that that's not the case. And I say every car is blue, and you want to prove me wrong, all you have to do is find one car that's not blue. right? So in other words, you don't have to show that every car is not blue. You just have to show one car isn't blue. So the negation of all the cars are blue is there is one car that isn't blue, or there exists a car that is not blue. And there might be more than one, but again, to prove me wrong, you only have to point out one of them. Okay, so there you have the proper way of negating a universal statement. The negation of a universal statement is an existential statement, where the second half, the part after the quantification, is the negation of the original part after the quantification. Okay, so that's how you negate a universal statement. So how do you negate an existential statement? Well, you can probably guess, but don't just guess, think about it. So there exists an X in D. By the way, I'm writing the word in because the book does, but I'll just make sure that we know. I think you've seen this before, that this symbol right here does that same trick. So there exists an X in D such that, oh, remember this discussion? After an existential statement is not a comma, but the words such that, which means I should go up here to this existential statement. I shouldn't have written a comma, I should have written such that. Let me fix that. The book uses a comma to stand for the words such that. I don't really like that. That seems very awkward to me. I've never seen anybody use a comma for such that. Okay, so let's get back to this. There exists an X in D such that Q of X. So again, that's like saying, I this time go out to lot number 2 and I say to you, there is a blue car in this parking lot. And you look over the parking lot and you realize that I'm wrong. How do you prove me wrong? I said, there's a blue car in this parking lot. How many non-blue cars do you have to point out? You have to point out every car and show that it's not blue, right? The negation of there is a blue car in this parking lot is every car in this parking lot is not blue. Okay? And that's very different than saying not every car is blue. So here's how you negate a universal statement. Here's how you negate an existential statement. Very, very important. Let's do now, this isn't really a third thing, but it's really a special example of number 1. Let's write down the negation of a universal conditional statement. Okay, so this is really, this is really a subset of number 1. Okay, let me write a universal conditional statement. For all x in D, P of x implies Q of x. And let's write down how we negate something like that. Well, it's a universal statement, right? It's a universal statement, just like that one was. So the rule should be the same as this, which is the universal quantifier turns into an existential quantifier. And what comes after such that? Well, let's look up there. What came after such that? The negation of this. So what should go right here? Should be the negation of this. Okay, so the negation of P of x implies Q of x. Now, you should know how to negate a conditional, so let's review that. How do you negate a conditional statement? Okay, let's review. Let's look at a truth table. So there's P implies Q. I want to negate that, which means every true turns into a false, and every false turns into a true. Okay? Now I'm going to erase that middle column. I don't need to look at that anymore. Let's bump this over. Okay. Let's look at that. This statement is true only one time. It's only true if P is true and Q is false. Isn't that the same thing as this? Let's write negation of Q here. That would say false, true, false, true. And let's write the conjunction of P with the negation of Q. So P and not Q. Okay? We can erase this column now. We don't really need that. Let's just look at what's there. P and not Q. That false right there means we're going to get a false here. This false right there means we're going to get a false here. Either one of these falses here would mean a false here. But in the second row, we've got true and true, which means we get a true here. Okay, now, isn't that exactly the same as this? It is, isn't it? So those two things are logically equivalent. So what we're getting at here is that the negation of P implies Q is the conjunction P and not Q. And that's what should be up there in our negation of the universal conditional statement. You get an existential statement where the last half of it is the conjunction P of x and not Q of x. Okay? And that is how you negate a universal conditional statement. The universal quantifier turns into an existential quantifier. The conditional part turns into a conjunction. The hypothesis of the conditional part does not change in the conjunction, but the conclusion of the conditional part gets negated in the conjunction. Okay? All right. So what have we covered? Negating universal statements, and then a subset of that is negating a universal conditional statement. And we've also done negating existential statements. Okay. Next little section. I want to review with you these words: contrapositive, converse, and inverse. You've seen them before, but I want to look at them a little bit deeper. Okay? So, let's say we have this statement. For all x in D, P of x implies Q of x. Or, if you prefer, if P of x, then Q of x. Okay? Let's say that is our original statement. Okay? All right. Now, this is called the converse. For all x in D, comma, Q of x implies P of x. Those are not equivalent. This is very important. Those are not equivalent. Okay? All right. Here is the contrapositive. Let's save that one. Let's do inverse next. The inverse of the original statement is for all x in D, if not P of x, then not Q of x. Okay, so converse, make sure you understand this. Converse is where you change the order of the implication. You reverse the implication. That's called converse. And you change the sentence when you do that. It is no longer the same sentence. They are not equivalent to each other. Inverse is when you keep the same order of implication, but you negate both parts. That's called inverse. Okay? And also very important is for you to understand that the inverse of a statement is not equivalent to the original statement. Very, very important. Okay? In fact, that's why we've seen before these things called converse error and inverse error. The converse error is when somebody replaces the original statement with its converse. That's called the converse error. And the inverse error is when somebody replaces the original statement with its inverse. Okay? Now, it just so happens that the converse and the inverse are equivalent to each other. Okay? All right, and then the last one is the contrapositive, which is where you change the direction of the implication and also negate both parts. It would say for all x in D, not Q of x implies not P of x. Now, that is equivalent to the original statement. Okay? I'm going to move this all over and give myself some more room on the left-hand side. Okay, so that's very important. I know you've seen those relationships before in chapter 1, so I won't say anything more about it. This is the second time you've seen it, but you really need to have those relationships down, okay? It's very important to know the contrapositive because it's equivalent to the original conditional. So that's very helpful. You see, anytime you have a conditional statement, you may, if you wish, replace it with its contrapositive. So that's a good thing to know. That's a good trick to have in your pocket. Okay? And you also need to know that you cannot replace it with its converse or inverse. But I will tell you that of those three, the inverse is the one that you see least often. Okay, now what about multiple quantifiers in one sentence? So statements with multiple quantifiers. Let's look at this. For all x in D, comma, there exists some y in E such that P of xy. Let me give you an example of that. How about if I write every number has an opposite. So in other words, that would be for all x in the real numbers, there exists a y in the real numbers such that x plus y equals 0. Okay? So it's a universal statement because it starts with a universal quantifier. The second half of the universal statement is an existential statement. So you could call this a universal existential statement. Okay? Let's write that down. A universal existential statement is a universal statement. It is not an existential statement. Part of it is an existential statement. Part of it is. Okay? The entire statement is not an existential statement. The entire statement is a universal statement. Okay? Now, how would you negate something like that? Well, technically you already know how, don't you? Because it's the first thing we did in this lecture. Negating a universal statement. So let's write this down. Negate this universal statement where the part after the comma happens to be an existential statement. So you technically know how to do this already. What should I do? The universal quantifier turns into an existential quantifier. And what comes after the words such that should be the negation of this, right? Look back up at the top. When you negate a universal statement, the universal quantifier turns into an existential quantifier. After that, you get the negation of what came after the universal quantifier here. So down here, the universal quantifier turned into an existential quantifier. And after that should come the negation of this. So in other words, right here should come the negation of there exists a y in the set E such that P of xy. How do I negate an existential statement? The existential part turns into a universal. So it'll be for all y in E, comma, and then after that should be the negation of P of xy, because that's how you negate an existential statement. Okay? So, summary. The negation of, for all x in D, there exists a y in E such that P of xy is, there exists an x in D such that for all y in E, not P of xy. Okay? So that would be like saying there exists a real number such that, let's call it x, for all real numbers y, x plus y does not equal 0. Of course, that statement is a false statement, but nonetheless, it would be the negation of the original statement. Okay? Now let's do an existential universal statement. So that's one like this. There exists an x in D such that for all y in E, P of xy. An existential universal statement is existential. It is not universal. Part of it is universal, but the whole statement is not universal. The whole statement is existential. Okay? How would you negate something like that? You can probably figure it out by now, but let's walk through it. Okay, the existential quantifier turns into a universal quantifier. After that becomes the negation of this. What is the negation of, for all y and e, p of xy? The negation is there exists some y in e such that not p of xy. And that's nothing new. That's just coming back again to the stuff that we did at the beginning of this lecture. Okay? So let's practice this now. Okay, here's a definition that you would have seen if you have taken Calculus 1. Okay? Suppose we have a function whose domain is all real numbers. The domain doesn't have to be all real numbers. I'm just making it that way to make things easier on us so that we don't have to keep saying the domain of f. We can just say the real numbers. Okay? So we have a function whose domain is the real numbers. And we have some c that is a real number. Now, here's the definition of the limit of f of x as x approaches c existing. The limit exists if, now let's read this all together. There is some L in the real numbers such that for every epsilon greater than 0, there is some delta greater than 0 such that for all x in R, if the absolute value of x minus c is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. That is technically a existential, universal, universal conditional statement. An existential, universal conditional statement. Okay? I want to walk through this with you and write down its negation. Now, in order to negate it, we'll make it much easier on ourselves if we translate it into symbols. It's way easier to negate something lengthy like this if you have it in symbolic form. So we're not going to negate right now, we're just going to translate. Okay? Starting right here. There is some L in R such that. Okay? There exists an L in the real numbers such that. All right, let's continue. For every epsilon greater than 0. Okay? For every epsilon greater than 0, comma. Even though there's not a comma in the original sentence, which is fine, but when I write it symbolically, I always put a comma after universal quantifiers. Also, notice that this doesn't say epsilon is in something. It says epsilon is greater than 0. That's just a fancy way of saying epsilon is in the set of positive numbers. See, it's much easier to just write that. Okay, all right, let's continue. There is some delta greater than 0 such that. Okay, there is some delta greater than 0 such that. For all x in R, comma. For all x in R. Yeah, let me fix that. Comma. If this, then that. Okay, so this implies that. Okay, now that we have the definition of limit translated into symbols, we can negate it with symbols, and then we will be able to write a sentence that will look like this. On the other hand, the limit of f of x as x approaches c does not exist if, and we'll be able to complete that sentence. Okay, so let's negate what we have up here. All right, it's not going to require anything new. Everything you need to know is earlier in this lecture. All right, we are negating an existential statement. So the negation of that will have a universal statement for all L in R, comma. What comes after the comma should be the negation of the rest of the sentence. What kind of statement is underlined in red? It's a universal statement. So its negation will be existential. And we will have there exists an epsilon greater than 0 such that. What comes after the words such that should be the negation of this. What kind of statement is that underlined in red? It is existential, so the negation will be universal for all delta greater than 0, comma. What comes after the comma should be the negation of this. What kind of statement is that underlined in red? It is universal, so its negation is existential. There exists x in R such that. What comes after the words such that should be the negation of this. What kind of statement is that underlined in red? It's a conditional. How do you negate a conditional? You get a conjunction of the hypothesis of the conditional and the negation of the conclusion. How do you negate the absolute value of f of x minus L is less than epsilon? We say the absolute value of f of x minus L is equal to or greater than epsilon. Okay, there we go. So now we have the negation of the definition of limit written in symbols. Now let's write it in words. The limit of f of x as x approaches c does not exist if for all L in the real numbers there is some epsilon greater than 0 such that for every and all are interchangeable, delta greater than 0, there exists or there is some x in the real numbers such that the absolute value of x minus c is less than delta, and a word that is interchangeable with and is the word but. It's not any better to you say but instead of and. I'm just saying you could say either one. The absolute value of f of x minus L is equal to or greater than epsilon. And there you go. This is what it means to say that a limit exists. This is what it means to say that a limit doesn't exist. Okay, that's it for today then.